So I'm going to be talking about radiation effects in nickel-based alloys and austenitic alloys. So as an outline of what I'll be presenting, I'll very briefly introduce the idea that the different types of radiation effects phenomena depend strongly on temperature. And for molten salt applications, that actually greatly simplifies the problem. It really comes down to being high temperature phenomena for molten salt reactor applications. After introducing the general concept of high temperature helium embrittlement, then I'll talk about some material specific behavior. So if you look at the general types of response of materials to irradiation, this is a series of microstructure images as a function of radiation temperature normalized to the melting temperature. The main takeaway from this is things change a lot with increasing temperature. That's all that you really need to know. For molten salt applications, we're kind of at the far right side of this figure. So all the stuff to the left, you can say that's kind of irrelevant because that's neither here nor there. Another way to look at this is in terms of the 5 key general radiation damage degradation phenomena that occur. You know, for light water reactors running at lower temperatures, we're interested in things like radiation hardening and embrittlement and phase instabilities and so forth. For molten salt reactors, it's arguably, there's a little bit of some of these things in the middle, but it really, I could make a strong case that it really boils down to just one of these 5 phenomena. So that's the good news, if you will. You know, 80% of the traditional radiation damage degradation phenomenon, you can kind of say, well, we can forget about those to first order. They're not really important. You're really only left with one, which is the high temperature helium embrittlement. And so just to kind of quickly say why we're not so concerned about things like void swelling, which is a usual major concern, you just look at some of the experimental data. And so here's a PE16 nickel-based alloy. Looking at its volumetric changes, swelling, as a function of irradiation temperature, and for 2 different doses in a fast reactor, going up to 80 dPa, which is well beyond what's considered for the designs that I'm aware of for the various molten salt reactor concepts. And it's also got some 20 dPa data. So 20 dPa data, you might get 1% change. You get that much just by going from room temperature up to the operating temperature. So this is very easy to handle from an engineering perspective. And by 80 dPa, it's 2% or something. These are, again, very easy to handle from a mechanical engineering perspective. So we basically, we have solutions where we're not really worried about void swelling. This is another plot just looking at, a variety of other alloys. And basically, if we start to worry about void swelling when it approaches 10% or so, and for things like nickel-based alloys like Inconel 600 or 800 or Hastelloy X, you're kind of on the order of 100 dPa level. These are very high doses compared to what I'm aware of for all the molten salt concepts. So I'm not, as a material scientist, worried about void swelling types of issues. So take away 80% of these radiation damage phenomenon. The one that I am concerned about is high temperature helium embrittlement. So if you just look at some old experimental results, looking at strength and more importantly, elongation, and as you go up to higher and higher temperatures, after the material has been irradiated, you see this dramatic decrease in the elongation, mechanical elongation of the material. And it changes from being kind of ductile, transgranular type of a fracture to where it's fracturing along the grain boundaries. So that gives you a clue that something is changing. And if you compare it with unirradiated material, this effect doesn't happen. So it's a radiation effect, if you will. But it's not the traditional radiation effect in that it's not really dominated by displacement damage. And I want to, from a scientific perspective, really emphasize that point. For all of the other radiation damage phenomenon, you can scale it according to displacements per atom, or dPa is this fundamental unit of how many times atoms get knocked off their lattice site, and that usually creates all kinds of havoc for the material. Because you're operating at high temperatures, so this is showing a couple of examples for nickel comparing the diffusion coefficient under irradiation, and the kind of the dashed line is the diffusion coefficient without irradiation. And this is plotted versus inverse temperature, so you have to cross your eyes to think about how to do this. So low temperatures on the right, high temperatures on the left in this plot. And so when you get up to temperatures that are of interest for molten salt applications, you see that the radiation-enhanced diffusion coefficient merges into the thermal diffusion coefficient. In other words, the vacancy concentration is the same under irradiation as it is thermally. So there's no radiation displacement damage effect to a large degree at molten salt reactor relevant temperatures. So if we're not worried about displacement damage, then why do we have a radiation effect? It comes down to the other thing when neutrons interact with materials, besides knocking off lattice is they can cause some transmutation reactions. And a particularly important one is the form N-alpha reactions that generate helium. And so we generate helium, and that helium at high temperatures can migrate, and it ends up migrating to grain boundaries. Because we don't have this radiation damage effect, displacement damage effect, this high temperature helium embrittlement phenomenon really is very weakly dependent on dPa. That's not the appropriate parameter to scale this by. But it depends very strongly on the helium content produced from the transmutation reactions. And if you're, have longer diffusion times, more time for the helium to reach grain boundaries, etc., it gets progressively worse. So as you go to lower strain rates, more relevant for actual plant operations, the problem becomes worse. And also if you apply a stress, which again is you're going to have some mechanical stress, even in a molten salt reactor, it's got to hold its own weight. That stress will also promote the diffusion. We're not worried about dPa. We're worried about strain rates. We're worried about just total helium content, and we're worried about applied stress. Is a summary of what happens to this. So let's look at some typical examples of what happens. These are tensile tests, so these are accelerated rate tests, at much higher strain rates than what would be relevant for the actual application. And it's a nickel-based alloy, PE16 again, at 650 degrees centigrade, implanted with helium. And this shows the various levels of helium that were implanted, up to about 50 atomic parts per million helium. And as you start decreasing the strain rate, going from 10 to the minus 7, 10 to the minus 5 per second, down to 10 to the minus 6 per second, you see this pretty significant reduction in the tensile elongation of the material, and doesn't have a huge dependence on helium concentration. That already at a couple of ppm atomic part per million helium, you're starting to see this fairly significant degradation. If you take one of these samples after it's been implanted and then aged and then tensile tested and put it in an electron microscope, and you look along the grain boundaries, it doesn't look very pretty. The grain boundaries are filled with these large helium bubbles along the grain boundaries. Obviously, it's going to be very weak along those grain boundaries because you've now lost a lot of the material in that grain boundary. And this is essentially the thing that we're concerned about with the high temperature helium embrittlement, keeping the helium from going to the grain boundaries. And so how do you prevent that? You don't put much helium in, knock down your neutron flux to as low as possible. But if you do an accelerated test, a tensile test, so you put your sample in a reactor and cook it for a year or so, pull it out, and then just do a standard tensile test, you're going to get a completely wrong, over-optimistic answer because you've not allowed enough time for that helium to diffuse to the boundary under stress. And so you're going to be completely misled. A good place to start is to look at actual data out of a molten salt reactor. So there's been one molten salt reactor, the MSRW. In the late 60s, there was studies looking at Hastelloy N, irradiated in molten salt reactor. This was to a pretty small fluence. Molten salt reactor didn't run for a whole long time. And this was just a portion of the time that it ran. They put a Hastelloy N sample in there. And so it was sitting unstressed. So that's a bit over-optimistic of the real case, running at 650 degrees centigrade. Then they came out and they tested a bunch of these samples at different test temperatures that you see here and at different strain rates. So as you go up in temperature, the helium during that short tensile test can more easily diffuse to the boundary. And as you go down in strain rate, your test gets longer. So again, you have more time for that helium to go to the grain boundary. And you can see a pretty dramatic reduction in the elongation of the material. That is down in single digits already at 10 to the minus 5 per second strain rates. That's a couple of orders of magnitude below where you're of interest for reactor applications for creep types of conditions. This general effect of strain rate has been seen in multiple materials. This is showing some results in an austenitic stainless steel, irradiated a couple of different fluences, producing on the order of 1 to 7 atomic part per million helium. Tested under tensile strain rates, it looks quite good. It's got 40% ductility. I'll take that any day of the week. But you start going down into more reactor relevant creep rate conditions, and again you're down in single digit elongations of this. It only took a very small amount of helium to do that. And this is actually a relatively low temperature, 550 degrees centigrade. If you boost that up another 100 degrees or more, where there's interest in some of the molten salt concepts, then this would just further accelerate this effect. Just showing some more results for neutron irradiated Hastelloy N, various fluences. I've included the DPA level, but I just want to emphasize again, DPA is not really the primary correlation parameter. It's really the amount of helium that gets generated in the material. Take that material after it's been irradiated, test it. So this was irradiated at either 280 degrees centigrade or 740 degrees centigrade, and you can test it at different test temperatures and start approaching, interesting molten salt reactor relevant temperatures. You see this very dramatic decrease in the ductility. Again, down in single digits for total elongation for this types of tests. And again, these were at tensile test conditions. So this is the best of all worlds kind of ductility that you would get out of this. Some more tensile data, about 2 atomic part per million helium, about a DPA. Again, DPA is not really the important parameter from this. So looking at uniform and total elongation for 2 different nickel-based alloys, 800H and alloy 617, the general trend in both of these, after irradiation, you have the unirradiated curve, and then after irradiation, you can see it's reduced, and it goes to around 0 at around 700 degrees centigrade or something. Again, these are tensile tests, so this is the best possible condition for these alloys, and not very much helium has been generated. So if we look at some additional data on type 316 stainless steel, looking at the creep ductility versus how much helium was being generated in the material, you see this general trend that the creep ductility drops from the unirradiated value down to very low values when you're approaching 1 atomic part per million helium levels in the material. If we look at some old scientific results of what's the effect of applying a stress on material where you have some implanted helium without any applied stress. And so this was an iron chrome nickel alloy tested at a relatively high temperature for short periods of time, just up to 60 hours. If you don't apply any stress, the helium tends to nucleate in the middle of the grains, and only a small fraction of it reaches the grain boundary. But if you put on a relatively modest stress, 20 megapascals, that's not a huge amount of applied stress, it's a night and day difference. So for the same test conditions, you now see the helium has been driven to the grain boundaries and starts forming already at 8 hours, 18 hours, 60 hours, just forming these quite massive grain boundary cavities in the material. When you're trying to quantify the relative magnitude, is use data that's most relevant for the reactor application. So this is a kind of a complicated plot with 4 different sets of experimental results in it. It includes the unimplanted creep rupture versus applied stress curve. So the blue is kind of your standard condition, no irradiation. And then they implanted with 100 atomic part per million helium, a relatively large amount, and they found some degradation. They implanted at room temperature. Well, room temperature, the helium doesn't diffuse, obviously, and so it's going to cluster or whatever. So then they tried implanting it at a high temperature where it can diffuse as it's being implanted, and you got a further, moderate reduction from that. And then finally, they did what would be more like the actual simulation. They implanted it in this cyclotron accelerator with an applied stress at temperature. And you see a pretty dramatic further reduction. So this is the most relevant condition for reactor conditions. These are the easiest tests to do. And unfortunately, there's too many journal papers that have used the easier way rather than the more reactor relevant type of an approach. So all that sounds like, what can we do to solve or mitigate this problem of high temperature helium embrittlement? The answer is in part by adding some second phase, the right type of second phase materials in there. And so taking an example from austenitic stainless steel, there's a set of curves here that are showing for 316 stainless steel, just this is a nice 90-year-old material that we all know and love, unirradiated, and then after implantation, you see this pretty dramatic decrease in the rupture time for 600 degrees centigrade types of tests. Now use a titanium modified stainless steel. This has a few tenths of a percent titanium added. That reacts with the carbon in the steel, forms a very fine precipitate distribution in the interior of the grains. And you can see, first of all, you get a much better unirradiated property. That's the open symbols compared to standard 316 stainless steel. And then the level of degradation when it's helium implanted is much smaller. So the overall net effect, if you compare in-beam at temperature creep behavior for the titanium modified material, it's vastly superior to the run-of-the-mill 316 type of a material. So that gives a big hint about the right way to try to make these materials is by introducing the right types of precipitates. It traps the helium, keeps it from going to the grain boundaries, and you have a very successful potential solution for this. The key in this case was these titanium carbide precipitates that trap the helium, keep it from going to the grain boundaries. So this idea also was thought about in the MSRE project. They saw the early results on the poor performance of Hastelloy N, and so there were studies that went on looking at adding titanium, hafnium, zirconium to Hastelloy N material. And so here's just showing one result from an Oak Ridge report, early 1970s. This is material that was irradiated at a quite high temperature at a modest thermoneutron fluence, and comparing the rupture life of this material tested at two different stress levels and two different temperatures, 650 and 760 degrees centigrade with 32 KSI and 12 KSI stress levels. But I think the key thing is to look at the rupture life versus the amount of titanium that was added. And you see this tremendous improvement in rupture life. It's going up, 10 to 100 times improvement in the rupture life just by adding a few tenths of a percent titanium to the Hastelloy N type of an alloy. With that, we have the playbook for designing the next generation of improved material is to add these precipitates in the material. And it really comes down to a way that you can quantify how effective the precipitates are in trapping helium and causing radiation damage recovery. And it's a concept called sink strength that in its simplest form, it's just proportional to the size of the precipitate and the number density of the precipitate. So a lot of really small precipitates gives you a very effective quantitative improvement in the helium trapping. It turns out that for making a higher strength alloy, the exact same principles also work. So if you look at the classic equation for dispersed barrier hardening, it also depends on the number density and size with a square root dependence. So if you say you want to limit your precipitate volume to 1%, So you have your precipitate volume fraction F. Then for best radiation resistance and for best mechanical strength, optimize this for high density of small precipitates in the material will give the best performance. And that's precisely what's been shown in many cases for radiation damage and also for, if you look at the nickel-based superalloys, et cetera, has shown to be very effective for getting higher performance and strength. So I think I've covered all this in the summary. So in the interest of time, maybe I'll stop here and we can move on to the next speaker then.
Thank you very much, Steve. Appreciate it.